Hello, everyone. As I am recording this, it is the middle of August 2026. And what that means is that about a week ago, maybe a bit more, Anthropic had an announcement that actually got a lot of airtime. It's about a change that they're doing to their generation algorithm to put a watermark into their text. There were a lot of big feelings about this. A lot of people were like, thank goodness. A bunch of other people got real mad and immediately started trying to figure out how to get rid of the watermark. I frankly did not have either of those reactions super strongly. But what I was excited about is this episode that we are recording right now because I was like, an invisible watermark in text? Oh, heck yeah. How does that work? And that is what we're going to talk about today. You are listening to Linear Digressions. The general idea of a watermark, just to back up in case this isn't something you've been following super closely, is it's a way that you can tell whether a given piece of text was generated by an AI or not. And the goal is that it's invisible. We'll talk a little bit more about what that means and how true it might be over the course of this episode. But the idea is it's not like, I don't know, a giant tag at the beginning that says AI generated text, because that would obviously give itself away. Or there were some jokes about maybe if you took the first letter of every sentence, it spells out a secret message, and that's how you know that it was watermarked by an AI. Also not how this works. There was some speculation that maybe what they were doing was they were encoding special invisible Unicode characters, like maybe special white space characters that when you render the text on the screen for your eyes as a human, it doesn't look like anything, but it's to the machines that are reading it, maybe a signature of the fact that it was generated by an LLM. But it's none of these. It is a way of actually generating the text itself. So the choice of words that Claude makes when it's generating an answer is explicitly impacted and affected by this algorithm. So we're going to talk about how this works. In particular, they say that our text watermark is a version of the SynthID text approach published by Google DeepMind in Nature in 2024. So I looked it up, and this is what we're going to be talking about today. This article, Scalable Watermarking for Identifying Large Language Model Outputs. Here's the general idea. For regular LLM text generation, it goes something like this. If you're familiar with LLM generation in general, this is going to sound really familiar. You have some preceding text, so that's all the tokens in the sequence up until the point T that you're at. That goes into the LLM. The LLM has some probability distribution of the next word it's going to generate, given all of the text that it's seen up until that point. It samples from this distribution and then outputs a token XT, the next token in the sequence, that gets appended onto the chain of tokens that it's seen so far. That is now the preceding text for the next go round. And so one token at a time is generating an output for you. And the core of it is this LLM distribution right here. So given everything that we've seen up to this point, what is the distribution of possible next tokens that we could have? What generative watermarking does is it messes with this process. So we start by taking a watermarking key. This is a private key that Anthropic has, but you and I don't. And that's fed into a random seed generator. And there's another thing that's fed into that random seed generator at the same time, which is the preceding text, the tokens in the context up to this point. So you have two inputs, the text that you already have and this watermarking key. That generates a random seed. Hold that random seed in your pocket for a second because we're going to use it. But let's go back to that preceding text now. You're going to take your preceding text and put it into your LLM, just like you do with the regular algorithm. LLM has some distribution of outputs, the next token that it could generate, given the text that it's seen so far. And now that distribution, along with the random seed that you are still holding in your hand from a second ago, those two are inputs into a sampling algorithm. And then from that sampling algorithm, the output token is selected. Output token is appended. You go back to the beginning. It's now part of the preceding text. You generate the next token in the sequence, and so on and so forth. So what we've done here is we've introduced a random seed generator and a sampling algorithm that then samples from that LLM distribution based on the random seed. We're going to talk a little bit more now about that sampling algorithm. Hold any questions that you might have about how to decode this, though. We'll come back to that in a second. Alrighty, so this is where it starts to get a little bit difficult to explain just in words. So if you are watching this on YouTube, you can follow along with the video guide, or if you have the opportunity to look up the paper yourself, you can kind of see this visually, but I'll describe it to you. What you're doing with that sampling algorithm is pretty interesting. You're basically putting your thumb on the scale in a very particular way. Let's talk about that a little bit more. So we had this random seed that we're going to be generating. Remember, that random seed is selected by putting a watermarking key and the recent context, like the last few tokens in the sequence, into a random seed generator. And then what that random seed is doing is it's not producing a single number or token or something as an output. What it's actually generating is a series of functions. Think of each of these functions as, at its simplest, a vector of zeros and ones. The way that those random functions are applied is that they're used to select preferentially from amongst the possible outputs. So in other words, let me give you a concrete example. Let's suppose that the recent context is my favorite tropical fruit is. In particular, let's say we're just looking at the last few tokens in the sequence. So tropical fruit is in this case. We know we're talking about tropical fruits, and there's a number of different ways that I could complete this sentence because there are many delicious tropical fruits. You could like mangoes, you could like lychees, you could like papayas, or you could like something called durian that I confess I have no idea what it is. And those are all going to be different candidates that you can sample from the language model distribution. Let's say mango happens to be the most popular of the tropical fruits, so you're going to get a lot of probability on completing that sentence with the word mango. Let's say after that, people like lychees a lot, so that might have a probability that's a bit lower, but still pretty high overall. After that, you have papaya, and then just with a little bit of the probability weight, we have durian down at the bottom. And let's say those are the four options that you have about how you can complete that sentence. So if we were doing just a regular generation task to select the next token from those four options, it would sample with the probability that each of them has according to the language model. So it's most likely to pick mango, but maybe 5% of the time it might select durian. So what these random watermarking functions are going to do is, again, remember, they're vectors of zeros and ones. So since we have four candidate options here, we're going to have four zeros or ones, and it's going to be each of those vectors is a mix of zeros and ones. And if the element at a given position is a 1, then it's going to select that answer. And if it's a 0, it's going to not select that answer. And these are going to be used in a tournament style sampling algorithm on this original vector. And that is the way that this bias is going to be applied, the bias of putting our thumb on the scale for how the sampling is going to work. So again, bear with me, this is a little bit complicated, but it's sort of fun. So now what we've got is we've got four candidates for how we can complete this sentence. And we have three different random functions, ones and zeros, and each of those have 4 elements apiece. Because we have 3 functions, we're going to have a 3-level tournament. So imagine something kind of like March Madness, if that's your thing, if you're into college basketball. So in March Madness, you have this bracket where you have two teams that go up against each other, and then you have single elimination, or even better, World Cup. We've just gotten off the World Cup. Everybody in the world watches the World Cup. So you have this tournament style play where it's single round knockout. You have team A versus team B, whichever one wins that game advances. And then you can have like several different successive layers of that, where each time the number of candidates is going to be reduced by a factor of 2 until finally you only have one remaining. So imagine now that you're having a tournament over all of those candidate answers, mango, lychee, papaya, durian, and who wins that tournament is going to be determined by these random functions that you've generated, the vectors of zeros and ones. So in a given position, if there's a 1, then the corresponding token is going to have an advantage in that round. If the other token that it's up against has a 0 from that same vector, then the token with the 1 wins. In the case of ties, you do a toss-up. You choose randomly. So let's suppose that our very first random function is 1, 0, 0, 1. So there's a 1 at the place of mango. That's the first one. 0 and 0 for lychee and papaya, the 2 in the middle. And there's a 1 for durian, way down at the bottom. And so now we're going to generate a bunch of pairwise candidates, like mango versus papaya, lychee versus durian, lychee versus papaya, durian versus mango, yada, yada. Generate a bunch of pairs so that we have all of these little tournament style games for them to play against each other. And then in each of those games, if we have a 1 against a 0, if we have a mango or a durian against a lychee or a papaya, then the mango or durian is going to win, because remember, those had the 1s in that random vector that we generated. On the basis of that algorithm, in each of the pairings of that tournament, 1 advances. Now we're in round 2 of the tournament. We have a second random watermarking function that we generated. Again, it's 4 elements, zeros and ones. It's going to be a different configuration of zeros and ones that we had in the first round. So let's imagine in the second round, our vector is 0, 1, 0, 0. So we have zeros for everything except lychee. Anytime you get lychee, lychee's going to win. Anytime you get something else, it's going to be at a disadvantage. Again, ties get just selected randomly. So coming out of that second round, if we had, as it happens, maybe we have a lychee that's made it through the first round of the tournament. Lychee gets selected to make it to the finals. And then maybe by way of illustration, let's say the other pairing in this level of the tournament is durian versus mango. Both of those have zeros in this random vector that we have for this level. So again, flip a coin and let's say that mango makes it through. So now we're in the finals and we have 2 candidates that are left, mango and lychee. Again, you'll have a new random watermarking function that gets applied at this level. New sets of zeros and ones. And if you have a 1 versus a 0, then the 1 wins. If you have a 1 versus 1 or a 0 versus a 0, again, flip a coin. So if you have mango versus lychee and you happen to have a random watermarking function where mango gets a 1 and lychee happens to have a 0, then your final output token for the entire sequence here is going to be mango. So that was a lot of work to do to get just one final output token out. Remember, we had to do generate a whole bunch of different tokens at the beginning, and then we have this tournament that they're playing against each other through multiple levels all the way through, and we get one out at the end. But it turns out that you can still do this in a pretty computationally effective way, so it doesn't end up making it any slower. And of course, what you get out at the end is still a perfectly valid answer according to the generation task. So if what you've put in as the context, remember, is my favorite tropical fruit is, having the next word in the sequence or the next token be mango is a perfectly reasonable next token to get generate. It's not doing anything that looks overtly weird in terms of the output that you're getting. What it's doing is it's just applying a little bit of a weighting function at each of those levels. And that weighting function, that bias in the final token that gets generated and the tokens that are winning the tournament along each step of the path, that is the signature that makes the watermark. By the way, just for your background, they have 30 levels of this tournament. And at each level of that tournament, it's looking at the previous 4 characters, or the previous 4 tokens, rather, when it's generating. What that means is that each time it's generating another token in the sequence, then that token is a chance for the weighting algorithm to be implemented. Because it's doing 30 levels of the tournament, it's not just you get some signal on this word independently, but you get 30 different signals on each word. So each one of the tokens that it ends up generating has a bit of a weakness in the signal. Like, it's not from a single token that you can tell unequivocally, like this was AI generated or it wasn't. Instead, it's many small signals that are starting to build up. So let's talk about decoding a little bit, because that's what we're starting to get into now. How do you decode this? What you need to start with is the text that you want to test, whether it has the watermark or not. So let's say you get a paragraph of text as output. You want to tell if this was generated by Claude or not. That's the text I'm talking about here, that paragraph. There's a watermarking key. Remember, this is the same watermarking key that Anthropic is holding and using in the generation process to create those random functions that we're using to weight the die when we are sampling from the LLM distribution. So you have the text, they have the watermarking key. Those go together into a scoring function, which basically gives you a probability, best guess, about whether a given token was watermarked or not. And what that scoring function is doing is giving you some signal about the likelihood that that individual token was coming from a process that looked like that random sampling, but then with the weights that we described as the watermarking process. So each of these tokens is going to give it a little bit of weak signal, but then you sum up that signal over all of the tokens in the text, and that gives you an overall score for the text. And then you can just threshold on that score. If that score is above some cutoff, that's in all likelihood generated by the AI. If it's below that threshold, if these are word choices that are not corresponding to a generation function, this like the watermarking algorithm we just said, then we said, yeah, these look like they were generated by some other process. Could have been by some other LLM. Anthropic's algorithm is not going to be able to tell you if a text was generated by OpenAI or Gemini, for example, just Anthropic in, Anthropic out. After that threshold is applied, they say, what's the overall decision? Was this text watermarked or not watermarked? And a few other things to note about this decoding. Just like the encoding, it's quite fast and it's quite computationally efficient. So that's a really important element of these watermarking algorithms. It's not just necessarily that they leave those signatures in the text about whether it was generated by an LLM or not, but also that can be done fairly quickly and in a pretty scalable way. The other thing I'll mention is, just given that this paper came out of Google, we've been mostly talking about this in the context of Anthropic because that's what everybody's been talking about lately. But Google themselves have been running this algorithm in Gemini for a couple of years at this point. So everybody's talking about Anthropic, but Google got there first. And of course, they're the authors of this paper. Some other important elements about this watermarking algorithm is how it actually ends up manifesting in the text. So one thing that's important is, even though you're placing some bias into your sampling algorithm, you're weighting the dice a little bit when you are selecting the next token when you use this algorithm, the overall distribution of the outputs that you produce still look the same as the overall distributions of outputs when you don't have any watermarking applied. So in other words, the final distribution that you get out looks the same whether you have a watermark or not. What it's not doing, and this might have been one of the other initial ideas that you had when you heard about watermarking, is, as you know, if anybody's worked with, I think Claude has the most distinctive voice of all the LLMs, but they each have their own version of this. Claude really has certain words that it loves to use. It loves to say things are happening quietly. It likes to say something is load bearing. Genuinely is one that I get a lot. Of course, there's the famous M dashes that LLMs love to write with M dashes. So this isn't necessarily saying like, oh, you talk like an LLM, or you don't talk like an LLM because we see that you describe something as quietly load bearing, for example. This isn't doing that. It's saying it's basically guaranteed to have the distribution of tokens that it puts out looks the same whether you're using this algorithm or not. So it's also not going to get rid of the things that are the quietly load bearing phrases. Still going to use them. Another thing that's worth noting about this is that the ability to weight the die basically lives in the space where you have a choice of different things to say. So the full example that we had at the beginning about my favorite tropical fruit is blank. The reason that that's a pretty good example is there's a number of different plausible ways that you could end that sentence. And that's in the context of information theory often referred to as entropy, like kind of the variation, the natural variation that your text allows. Something that would not be a high entropy sentence might be something like how the next token in the sequence, if what you've had so far is the capital of France is blank. Like there's really only one right way to end that sentence. Like you're going to say Paris. I guess you could say, of course you could say something else, but you're not going to find a whole lot of that in your sample text or something. So that would be an example of a low entropy distribution where all of the probability is massed around just a very small number, or in this case, like one next output token that you expect to see. So if what you're generating, if the type of text that you're generating with the LLM is high entropy, then that's where the watermark is really going to be strong because it has the flexibility to make those different choices that'll be characteristic of the fact that it's sampling. If you have a sentence and the sentence is the capital of France is Paris, very difficult to tell if that was generated by an LLM or a human, I would say in general. But also maybe that's where the stakes are relatively low. If you read the sentence, the capital of France is Paris, you probably don't care as much whether that was written by an LLM or a human relative to other types of writing that you might see. The other thing about it is that your ability to detect whether something was watermarked tends to get much better for longer samples of text. So for example, they have results where they looked at all the way from below 100 tokens in the text sample up to 400 in the Google paper. And if what you've generated is something like 20 or 30 or 50 tokens, then it's actually pretty hard to tell whether it's watermarked or not. There just isn't as much information in there. You need lots of small signals in order to detect the presence of the watermark. And if you just have a few tokens that you're looking at, you don't have enough signal to accrue. And so your ability to pick up on the watermark is relatively low for those small generated samples. But by the time you get up to 400 tokens in the sequence, so this is like roughly a page of output text, then you're getting at the probability of being able to detect it as something like 80-90% true positive rate if the false positive rate is 1%. So in other words, it's saying if you have 400 tokens of text, you're pretty darn likely to be able to detect the presence of the watermark. So that's another characteristic of these algorithms, is that they tend to give stronger signal on longer sequences of text. And then the last thing that I'll say is that what you've probably gotten from this whole conversation is that the watermarking really works in the individual words that Claude selects. So if you wanted to do something like remove the watermark, which many people are now have algorithms floating around out there that purport to do this, then the fastest way to do that is to mess with the word choices. So if you have a page of LLM generated text and you start to go in and you change a bunch of words to be basically synonyms with themselves, then that's going to start to mess with the watermark pretty quickly. Now, I would argue that if you're going in and changing a whole bunch about the LLM output, then that's actually a sign that it's no longer as purely LLM generated as before. So that editing process is arguably rehumanizing the text, making it valid to say that this is less of an LLM text at this point, that it has a heavier human hand behind the generation process. And so seems like relatively fair that the watermark would be harder to detect in that case. The point here is that you or anyone else that you know, if you want to go in and heavily edit your LLM text, then you can absolutely do that, of course. And that is also going to weaken the watermark. And I would expect that the degree to which the watermark is weakened is probably proportional to how much of a heavy hand you take with the editing. So I wouldn't necessarily call that a bug per se. It's probably closer to a feature, or at least just a characteristic to be aware of. But given the generation process and the whole idea of sampling in a specialized way, makes some sense that then if you start messing around with those word choices, you're undoing that watermark. So now you know a little bit more about Claude's watermarking process. Anthropic has said that in addition to watermarking text, they're going to, at some point, this is not out as I record this, they're going to release a watermarking detection API type functionality as well. So they would be able to tell you, you give them a piece of text, you want to know if it's watermarked, they can run it through that algorithm and give you some sort of score that comes out. That's not available right now, but you could see how potentially that could be a pretty interesting capability if you think you're getting AI generated content and you want to be aware of that fact at the time. Anthropic will, at some point in the future, be able to tell you whether they were the ones who created it at some point. So that should be kind of interesting, and I do sort of suspect, and I wonder how that's going to change the way sometimes people are using LLMs right now, pretending maybe a little bit more that they themselves are the human authors of stuff where they're having the LLM write it for them. I really wonder how that AI slop economy is going to do once there's a detector out there that's pretty easy to use for at least one of the large sources of LLM generated text. Speaking of detecting AI generated text and generating text with AI and so on and so forth, if you are interested in getting a written version, kind of a Cliff's Notes, the distilled takeaways from the stuff that we cover on linear digressions, or you're interested in other fun little tidbits that we find along the way, not necessarily content that's covered in these episodes, but that we just find interesting, head on over to Substack, look for linear digressions. Full disclosure, absolutely use Claude to help me summarize the points that I'm making in these episodes. The content itself is very human generated, but anyway, I've got a little Claude friend that helps me distill that into material that I think folks who like these episodes may enjoy. So if you're interested in being on the newsletter, come on over to Substack and look for linear digressions. If you want to subscribe to the podcast, you can do that on iTunes, Spotify, anywhere you get your pods, linear digressions. And for some of the content that we do, especially stuff that lends itself well to visual accompaniment, including stuff like this episode, experimenting with some material going on YouTube as well. So if you are finding us through YouTube, welcome. Good to see you. And if you are a longtime podcast listener, but you think you'd like a visual medium, head on over to YouTube and you can check us out there as well. So with that, I'm going to sign off for the week. Thank you for going on a relatively technical, but I think pretty fun deep dive into how this watermarking generation actually works. I hope you learned a little bit, understand a little bit more, and I will talk to you next time.